Benoit Guillot. Benoit is a professor at CRM2 laboratory of Lorraine Université at Nancy. He holds a master's degree in physics and biocrystallography and earned his PhD under the supervision, of course, of Professor Claude Lecomte. His doctoral research is focused on the first experimental electron density analysis of a large protein of pharmaceutical interest, human aldose reductase. Following a postdoctoral fellowship at the Hauptmann Woodward Institute at Buffalo, he continued his academic career at Nancy, specializing in the development of methods for charge density studies of biological macromolecules, particularly those based on the transferability of density parameters. He's also a co-author of the MOPRO suite program package and the author of MOPRO Viewer, a software dedicated to computing and visualizing electron density derived properties. So Benoit today will talk on quantum crystallography of macromolecular systems, applications, and recent developments. The screen is yours, Benoit, please.
The screen is mine. Thank you very much, Christophe, for this kind introduction. Thank you for the invitation, of course, and I cheer everyone in the audience, including, of course, people I know. I recognize some names, so it's very cool. So I will speak today about quantum crystallography for macromolecular systems, and I will show applications on recent developments. And then to be a bit more precise about the outline of my talk, I will start by doing, how can I say that, a short review of some selected quantum crystallography application to macromolecular systems, a review of, studies I selected for various reasons. And I will end up my lecture by introducing something we just published, we just submitted, very recently, is the development of a new descriptor for protein electrostatics, which is based on the topology of the molecular electrostatic potential. So let's start by, I'm a bit lost between my screens, sorry. Let's start by quantum crystallography approaches for proteins. I had to do a bit of bibliography to prepare my speech, as you can imagine. And at first, I would like to mention this very nice, very recent review by Anna Kroschuk and Alessandro Genoni that they published last year in Acta Christ, which really gives a very nice overview of modern quantum crystallography approaches. Very nice. So I used this paper on some other, and at a point, I somehow realized that we can actually split the quantum crystallography approaches applied to macromolecules into two big categories, into two big bags, I would say. The first one is the one related to refinement of protein structures, or say related to whatever is connected to the structural determination or the structural refinement of the protein. And in this part, of course, we find what are probably the flagships of quantum crystallography nowadays, which are the Hirschfeld atom refinement, of course, in which aspherical quantum mechanic atomic scattering factors are computed in the middle of, in between these square refinement rounds. And this method is extremely powerful for small molecules, but unfortunately, it has been shown not to be applicable in its basic version, I would say, to macromolecules. Recently, it has been attempts of combining or creating some kind of hybrid methods in which the extremely localized molecular orbitals developed by Alessandro Genoni are coupled with the Hirschfeld atom refinement approach. Using so transferred, I will try to use my pointer, sorry, I will do, so I guess this way. Yes, you see my pointer? Okay, fine. So they use transferred electron densities in the form of extremely localized molecular orbitals. And in this case, it has been shown in this paper that the Hirschfeld atom refinement can be applied actually to small proteins, but still at the expense of a very high computational time, because they mentioned the chromin refinement at 0.5 angstrom with a duration of more than 9 days. So it's quite a lot, but still it becomes feasible actually, that kind of approaches for proteins. Of course, the other big method in our field, big modern methods which combines in a very nice way experimental information and quantum chemistry computation is the X-ray constraint wave function approaches, which are not applicable to protein, to the best of my knowledge. I hope being right. And of course, I must mention all the what is called the quantum mechanical refinements, in which quantum mechanical restraints are computed, especially to define more properly the geometry of ligands and to improve the obtention of correct protonation states of residues in protein. And this one is actually applied. I will not talk a lot about that because I think our next speaker will actually speak about these methods, but it is important to know that these quantum mechanical restraints are actually included now in the Phoenix program, which is very famous for macromolecular refinement. This is the program which is the most used these days for macromolecular refinement. And of course, I want to mention the methods on which I am quite specialized, which is attempts of direct electron density refinements against subatomic resolution X-ray diffraction data for proteins. So refining electron density against high resolution. So this is the first part on which I will not discuss so much except for the last point. The second big category I want to mention is studies where people were actually interested into direct properties of proteins or protein ligand complexes. Such approach are, of course, pretty much structure-based in the sense of they rely on the knowledge of full protein structure, which were properly prepared, which means full protonation states, of course, which means a special treatment of alternate conformations and so on. And these methods are mostly based, these methods are mostly based on transferred atomic or transfer group parameters, among which we must mention, of course, electron density parameters from in the multipolar model using various electron density databases that I will discuss a bit later. But I must also mention the possibility now to transfer atomic or group polarizabilities. We did that some time ago with my former PhD student, Theodoric, using averaged atomic polarizabilities, but Anna Kroschuk very recently in her group published several papers in which she introduced the new Gripol database of transferable anisotropic group polarizabilities this time. So again, it's transferable properties. And in terms of transferable properties, I will also mention, of course, again, the extremely localized molecular orbitals developed by Alessandro Giannoni at the time he was in Nancy. So among all these methods, there is one keyword which comes several times, is the notion of transfer of parameters toward a macromolecular structure, a protein or say a nucleic acid structure. This highlights, of course, there is something which is okay. This highlights the importance of what we call the transferability principle that I will describe now briefly in 2 slides. So I find important to remind where does come from this transferability principle. It has been actually introduced for the very first time in the 90s, in 1991, in a paper by Brock, Dönitz, and Hirschfeld. They studied actually lattice dynamics of aromatic molecules like perilene, naphthalene, and anthracene, and so on. And they used multiple parameters for perilene, and they used these multiple parameters to improve the thermal displacement parameters on the other molecules, for which the data did not allow to refine actually multiple parameters. So it was the first actual use of the transferability principle in the objective of improving the description of the thermal displacement of small molecules. And this idea actually was the seed, I would say, the root idea from which Virginie Pichon-Pez, Paul Lecomte at the time decided to build a very first database of multiple parameters associated to various atom types all described, all written in the very well-known multiple atom model. So I just remind the equation here, highlighting in red the parameters that are actually stored in the multiple, in the transferable multiple databases that I'm talking about. So the valence populations, the multiple populations of the atom type, and the kappa kappa prime contraction parameters. The idea of such databases were initially to, the first idea was really to focus on macromolecular systems. So the first database was actually built to extend what we called at the time the charge density study field to the world of macromolecular biocrystallography. So behind that, the idea is really the following. We have atom types which are described, as multiple pseudoatoms, and several tools were developed in order to reconstruct macromolecular electron density in matters of, literally in matter of seconds, from which we can expect to gain many properties or many insights about the structure and the function of the macromolecule. Here is a very short illustrative example which shows that using two atom types, the one of the carbon in the carbonyl group and the one of the oxygen in the carbonyl group, allows to reconstruct the deformation density of a carbonyl group. I will go briefly through the available databases, so I will not go into too much details because the literature is extremely dense about that. There is the University at Buffalo Pseudoatom Databank, so the very well-known UBDB, created by Paulina Dominiak, which is based on DFT calculation, experimental structural factors, then chemical clustering, and then averaging. Then the UBDB was considerably extended toward the MATS database, which is the multipolar atom types from theory on statistical clustering, which is also based on DFT, but this time using a very advanced method of statistical clustering to define the atom types and then averaging of the multiple parameters. There is also the generalized invariant database, which was created by Birger Dietrich, which relies on model compound without any averaging this time. And the one we created, LMAM2 library, the last version, which is based on experimental data, uses chemical intuition clustering plus outlier reduction on multiple parameters averaging at the end. The idea of all these databases is that they can be used to improve structural refinement. This is the nowadays very well-known TAM approach, popularized also by Paulina, by the way. The idea is also to gain access to all a wealth of electron density-derived properties, such as topology, QT, IM, electrostatics, and so on, and also to define a starting point for multiple refinement of protein charge densities. And this is the point on which I want to spend a few minutes now. So, of course, the PDB has some diffraction data set for proteins which are clearly less than 1 angstrom, clearly less than 0.7 angstrom, and so on, but they are actually quite scarce, explaining why that kind of study in which multiple parameters are actually refined against protein diffraction, protein crystal diffraction data is extremely rare. I must mention the Crombin study, which was done by my colleague Christian, who is just there, on the Crombin protein, also a trypsin at half an angstrom resolution by Andrea Schmidt. But I want to spend a bit more time about the charge density refinement of the aldose reductase ternary complex. It was a long time ago, but still, I want to mention it because it is still nowadays by far the most favorable ratio in between the actual resolution of the data. Sorry, I think I've lost my pointer now. Okay, it's actually the best case in terms of ratio between the size of the protein. It is a 36 kilodalton protein on the actual resolution of the diffraction data. So this structure was extremely appealing, I would say. And that what we did is that we transferred the multiple parameters from the LMAM library and we performed the constraint refinement of the charge density in the sense of all chemical equivalent atoms were constrained to be equivalent during the refinement. And we focused on kind of substructure in the middle of the protein. The results of this refinement was quite satisfactory in the sense of In regions with very low thermal displacement, the initial, as you can see here on the right, so sorry, here on the left, sorry, you can see the residual electron density peaks on the it's on the tyrosine 48, it's catalytic residue, which is on the same quality that can be expected actually for a small molecule. And this is the final density. So we performed this refinement, and what are the outcomes of such a refinement is that we observed, which is actually always observed in such studies, is that we observe a small but a systematic decrease of the thermal displacement parameters. We observe a very significant statistical improvement of the crystallographic agreement factors, and we were able to compute the electrostatic potential from the refined density, which compared quite well with an equivalent DFT calculations, which was made at the time by Nicolas Muset using the Siesta code around the tyrosine residue, which is catalytic. So it's a very good qualitative agreement. Of course, all this is at the expense of final static density, which appeared quite attenuated in this case. But still, it was the very first big study of this kind against X-ray data for biologically relevant protein. We used constrained refinement. To the best of my knowledge, there is only one study in which people reported the actual individual refinement of multipolar pseudoatom against X-ray data. Is the one published by the group of Kumio Miki about a high potential iron sulfur protein, which was measured at almost a bit better than 0.5 angstrom resolution. They actually studied iron sulfur cluster in which this managed to to get access about the deformation of an iron atom in the cluster, showing static deformation density that they attributed to 3D orbitals of the iron. And they also successfully characterized the two subclusters of this cuboid by showing that the topological charges on the iron are significantly different between the two clusters. And indeed, taking a look to this data, actually, they show very, very nice residual density before the multiple refinement, and then quite clear residual density after the refinement. So this is really the only case, to the best of my knowledge, in which the charge density refinement of a protein means actually individual pseudoatom charge density refinement. So it was published in Nature, and I guess this is the reason why. I want to mention also briefly a study which is probably being published very quickly. I hope, at least. It's about the revisit of the 0.5 angstrom data of zDNA dodecamer. It was published initially in 2011 by Brzezinski in the group of Mariusz Jaskolski. And then a bit later, Maura Malinska and Zbigniew Dauter, they published a study in ActaChrist in which they performed the TAAM refinement of this particular structure. And again, they obtained better statistics, lower B factors, lower residual density after the TAAM approach versus the independent atom model refinement. At a point, we can honestly wonder why all proteins, as soon as they are obtained at a resolution better than 1 angstrom, why we don't use systematic this approach to better structure at the end? Because now the tools which are provided either in our side or from the from the people in Paulina's group, for instance, the tools are very, very well done, and it's very it has become very easy to do, by the way. So we took this data back, and the idea was to perform the constrained refinement this time. So again, to refine the experimental data, to refine against, the experimental data. So it's kind of a revisit. Indeed, taking a look to the residual deformation density, they shown after the higher level refinement, they shown classical features that you always observe in most of the very high resolution protein structures. If you take a look to the residual density, is that they are very variable in the sense of sometimes, let me show you with the pointer, sometimes bonding peaks are not present at all at the given control levels, or oppositely, they are very strong on some bonds, for instance, in between C6 and N1 and so on. So very variable residual densities, which disallow totally the refinement of individual pseudoatom in this case. So we went for a constraint refinement as usual. And in this case, it appears feasible because, as you can see on these pictures, which show the averaged residual density on the ordered residue or the order heterocycles of the ZDNA molecule, we show much more realistic bonding electron densities. And these residual densities, averaged, are actually the information against which we perform the constrained multipolar refinement. So what are the outcomes of this soon to be published refinement? Of course, we obtain better statistics, lower B factor, lower residuals after the refinement. As usual, it is always observed. But this time, the most interesting outcome was different. Actually, by doing the higher order refinement, which is a method usually used, which is used usually in small molecules charge density studies, this higher order refinement allows to locate an unspectated disorder on one heterobase, which extend up to the, you can see here, which extend up to the ribose group of a given cytosine residue. As you can see here, the bonding electron density peaks, which were initially attributed as deformation density, were actually a very slightly displaced deformation, alternate conformation of this particular residue with the peaks which appear much, much sharper after the higher order refinement. So in terms of outcome, we were managed to model this disorder with approximately 10% occupancy. We obtained a decent electron density model, actually quite acceptable. And we were able to characterize, by the means of the quantum theory of atoms in molecules, very interesting interactions, systematic, actually intramolecular interaction within the ZDNA strand, especially these two guys here, as you can see, these two critical points, which corresponds to O4 prime of the ribose group, which interacting with the p electrons of the previous guanine residue in the sequence. And this kind of interaction were actually already studied previously. This is an example when typical. This is an example when typical quantum crystallography methods, at least what was in the experimental side of these methods, provide actually extra information to the when compared to the standard structure determination. Okay. So I think I'm going to switch some parts of my slides because I'm already too long, right? At what time did we start, by the way? I didn't make the chronometer.
It's okay. You can go.
It's really okay. Do not worry about time.
Fine. Fine. Thank you, Christophe and Paulina. So the other kind of studies I want to mention are the ones which are based on fixed transferred electron density, from which authors expected to gain chemical intuition in the form of electron density descriptors and so on. I want to mention this one that we did some time ago in collaboration with Alice Vreeling in the University of Western Australia. It is a cholesterol oxidase, which oxidases cholesterol, as the name says, with the help of the flavine adenine dinucleotide cofactor, which is, you don't see my pointer, which is here, okay. No refinement, even constraint was possible because we shown in this paper the effect of thermal smearing on the deformation density very clearly by considering average density versus the equivalent B factor here. But nevertheless, what was interesting is that we shown that the transferred electron density, allows to reach very nice electrostatic complementarity, better than the one we obtained using Amber point charges. This is the complementarity between the electrostatic potential generated by the receptor on the FAD surface and the electrostatic potential generated by the FAD itself on the same surface, as you can see. It's the complementarity. So electrostatic complementarity is, of course, something that we can very easily study and reach using transferred electron density parameters. But we can go far beyond this. Indeed, we get access to many different kinds of descriptors from the quantum theory of atoms in molecules, for instance, and also especially on electrostatic interaction energies, especially between receptor and the ligand atoms. Here I show the correlation between electrostatic interaction energy obtained by symmetry adapted perturbation theory, so it's purely quantum mechanical approach, versus the one we computed using the transferred electron density parameters. And we did that on a subset of the Nancy 2021 benchmarking dataset, meaning we did that computation with comparison over more than 5,000 organic dimers, and we obtained a very, very nice correlation with a mean absolute error of 1 kcal per mole and RMSD a bit more than 1.4 kcal per mole. Of course, I show that for the LMM2 database, but believe me, if we do the same with the UBDB or MATS database, we will get very similar results, and probably even better because of the origin, the theoretical origin of both SAPT and UBDB multipolar parameters. So this is the strength of the transferred approach actually toward proteins, and this coupled with the fact that the multiple model actually gives the possibility to examine electrostatic interaction energies versus residue, versus pseudoatom, versus groups of pseudoatom, or even versus a portion of the sequence of a protein. This is extremely strong. Moreover, the calculations can be very fast using the EPMM methods, and can be even faster using the new analytical approach that we implemented in MoproViewer. So this approach was published by Nguyen in 1918 and implemented in MoproViewer by Vedran Vukovic, a former PhD student in our group. And you can see, for instance, here the list of interaction energy between the ligand, part of the list, I would say, between the ligand and the various residues. And to give you an idea of the performance for 575 residues, all interaction energy can be computed in much less than 10 seconds using this software. Okay, so using this approach, using the transferred electron density parameters, many studies were published in the literature. I will mention very briefly 4 of them. The first one, I always mention it because it was stunning at the time. It is the study of inhibitors of the influenza and the ramidinase, made by Paulina in 29. It involved 70 PDB complexes and more than 43 inhibitors. I remember at the time, honestly, I was very impressed by it. And even more impressed that they actually managed to obtain very interesting biological information about that. For instance, that the conserved residues among the complexes represent at least 85% of the total electrostatic interaction energy. And they also explain the effect of a particular mutation in this protein from an electrostatic energy point of view, explaining why glycerol-containing inhibitors were more efficient, actually, in this protein. So very kind of funding study, really. The second one I want to mention is the one of the sunitinib. It is a small molecule which binds to tyrosine kinases. It was published by Maura Malinska in 2014. And it is very interesting because in this study, they used several receptors from the PDB, well prepared and so on, but they used electron density of the ligand coming from a small molecule charge density experiment. So they managed to merge to the kind of hybrid approach in which small molecule high resolution crystallography was used to augment what we can get as information in macromolecular crystallography. And they studied interaction between sunitinib with conserved residues in the binding pockets, of course. And they shown, for instance, that there is a 3 residue triad which is conserved in all tyrosine kinases, and then the electrostatic interaction energy with this triad is highly conserved also. And they shown also the importance of more interactions that were usually considered in the literature. The third study I want to mention is very recent. I wanted to show it because it proves you that this approach are absolutely contemporary research. This was published 3 months ago in the group of Professor Wozniak, actually. And it is very nice because it tackles a very important biological problem related to the selectivity of non-steroidal anti-inflammatory drugs for cyclooxygenases 1 and 2. You know, they use 4 ligands, including the well-known ibuprofen, which is the one which gives stomach pain if you take too much because of its lack of selectivity between COX-1 or COX-2. So they compare very thoroughly all binding modes in these proteins of all these inhibitors, and they've shown that in terms of electrostatic interaction energies, again, their results are in total agreement with the low selectivity of ibuprofen for the two receptors. They show that the high affinity of another inhibitor, the celecoxib, and meloxicam are indeed for COX-2 and not for COX-1. And they shown also what are the key residues for electrostatic interaction energies. So it's a very nice study because it focuses on very well known, very well long-standing biological problem. Very impressive. I want to finish this very quick review by a last, if I can make it pop, sorry, yes. A last study, so back in time in 29, I want to introduce this study to you, to remind you this study to you, because it will help me to make the transition with the remaining part of my talk, actually. It is a study of a phosphate binding protein that we did in Nancy at the time. We had crystals, structural self at two different pH, 4.5 and 8.5 pH, so acidic and basic pH, basically. And we shown from high-resolution crystallography that both of these structures, whatever the pH, binds monobasic phosphate, HPO2-, despite the fact that at acidic pH, this form is way less present than the other one. And we complemented this study by showing that actually the electrostatic potential in the binding site present on very high complementarity with monobasic phosphate only. And we shown also the presence of a low barrier hydrogen bond, thanks to high resolution data again, which enhances this this very high, we say, selectivity toward this monobasic, dibasic form, sorry, of the phosphate. So I want to mention this study because actually there is a small story behind it. By high resolution crystallography on our so what we call now quantum crystallography methods, we shown that the phosphate binding protein bind only dibasic phosphate, whatever the pH, and that the binding site presented extreme hydrogen bond selectivity and electrostatic complementarity. But at this time, the biochemical measurement disagrees with that. At the time, measurement shown that phosphate binding protein, they had similar affinities for both forms of phosphate, whatever the pH. And to explain this, they say that probably the binding site is very adaptable, and then it can very much accommodate for whatever kind of phosphate in the binding site. And this controversy was solved 10 years after by people in a group of Lorraine Guillot. So I guess you know them. They are doing very serious business in computational biochemistry, of course. And they did a molecular dynamic simulation of this system using their amoeba polarizable force field. And they shown very nicely that actually the bindings affinities which were equivalent were actually just apparent because of a bad accounting for the buffer solution. And they actually confirmed what we hypothesized before, that the phosphate binding protein actually prefers by far bind to the dibasic form of phosphate. You can see here, for instance, this is the good binding form with the dibasic form, and here the binding site is totally displaced. And what I want to show you using this is that we actually proposed this in the paper we published in JACS, notably because of the interpretation of this particular picture that I show you here. This picture which shows very intuitively the extreme complementarity between the potential that you can expect from a phosphate group and the one computed within the PBP binding site. So this allows me to go to the next last part of my speech. I think it's going to be okay in terms of time. What we did on the PBP was based on the interpretation of a representation of a given property coming from electron density. And actually, there are in our field a lot of electron density descriptors which can be represented and that we actually interpret. There are, for instance, the bond paths and critical points, the reduced density gradients, isosurfaces in the NCI analysis, the fingerprints plots, various kinds of electron density, various kinds of electrostatic potential. All these are actually interpreted. All these properties are interpreted from graphical representations. Of course, they bear quantitative information as well, but still the graphical information, the graphical representation is a source of intuition, is a source of interpretation to my point of view. So this is why we propose a new graphical electrostatic descriptor, which is based on the topology of the electrostatic potential. So this electrostatic potential, I will not go into details because it has been discussed by Enrique Espinosa in this particular event last year, I think. And there are plenty of papers, especially by the group of Sridhar Gadre or Kumar and so on. So the idea of the electrostatic potential topology is, of course, to locate potential critical points using regions where the gradients of the potential is equal to 0, and to locate critical points, as usual. But in this case, the 3-3 are electrophilic sites, so they are actually maxima. The minima are nucleophilic sites, and there are also saddle points, but whatever. This topology allows to define zero flux surfaces of the potential, which partition the molecular space into topological basins, just like the electron density topological analysis. But the main difference is that as we use the gradient of the property, in this case, the gradient of the potential is actually a physical property. It is the electric field. So it means that we can actually discuss or consider the topology of the potential as in terms of electric field lines. However, in case of macromolecules, as you can see in this picture, I hope you can see it, the vector field which represents, the electric field is a vector field, and within protein it is a very, very high degrees of complexity, as you can see. So our idea is really to rationalize this, to propose abstract descriptors of the distribution of the electric field lines in macromolecular structures. So I will start by a short reminder of a very important property in this field, which is what you call the primary bundles. As you can see in this very simple model, it's just a simple dimer between methanol, on a peptide molecule in which we transferred our density parameters. You can see electric field lines which are emanating from protons, so 3-3 critical points, and all converging toward lone pairs of this oxygen atom here. So all these field lines correspond to what we call primary bundles, a bundle of field lines joining a given pair of nucleophilic, electrophilic sites, right? Those are primary bundles. Of course, representing them in line field, using field lines, may be less clear than representing simply the volume which are bounding this region. So here, the primary bundles are closed in this case because the system is neutral, and they are represented as simple volumes corresponding to each pair of 3-3 and 3+3 critical points. Okay. But what we are relying on for our descriptor are the nucleophilic and electrophilic influence zones, which are being introduced by Ines Imata in this paper. These zones are the union of primary bundles associated to a given electrophilic or a given nucleophilic site, unions of bundles. Meaning that, for instance, taking the same examples as before, in this case, we have 3 primary bundles of this particular hydrogen atom, the one which is hidden behind the surface here, okay? 3 bundles, so line fields going from this hydrogen to the lone pairs, and from this hydrogen to the p electrons of the peptide plane. Here we have primary bundles of these particular oxygens. Again, line fields coming from protons and converging toward the lone pairs of this oxygen atom. And what are these nucleophilic and electrophilic influence zones? They are the union of these bundles. So here, for instance, we can see the electrophilic influence zone of this particular hydrogen atom, and here you can see the nucleophilic influence zone of this particular oxygen atom. Of course, you can see that the space can be partitioned actually either, or at the same time, if you want, either into nucleophilic and electrophilic influence zone. And this is an example, still with the same system, the small dimer here, in which the space is filled by electrophilic influence zones of the various sites in the 2 molecules. And it is a full partition of the space, just like in the topological analysis of the molecular electron density. So all these regions, all these influence zones represent the regions of space which is under the electrostatic influence, under the influence of electrostatic forces of a given chemical group within the system in example. So I will go a bit faster now, if you don't mind, because I think I will be a bit too long, but still, I will show you a precise example of this development in the protein structure. As an example, I will use not this small dimer as before, but a true protein, which is the fatty acid binding protein, something we studied some time ago with colleagues in Strasbourg, using both X-rays and neutron data. There's a joint refinement of a deuterated structure, allowing us to determine a very nice ordered cluster of water molecules in the binding site. So the ligand is a fatty acid. This is the oleic acid here. It is binding the protein with the carboxylate head, which is tightly anchored to some residues at the bottom of the pocket. And we published this study. Checking, of course, the complementarity of the potential between the ligand and the protein, all what can be done actually with the transfer electron density approach. And then we show that the presence of a very strong electrostatic potential gradient in the binding site, which is being experienced by the ligand. And of course, a strong V of R gradient means electric field. The presence of these water molecules were quite puzzling people at the time, and they were presumed to facilitate a favorable electrostatic environment, say favorable electrostatic environment, okay, in the binding site. So what we can do with our descriptors using this model is the following. So this is a simpler view of the protein. You see the binding, you see here the oleic acid, and here I just added one particular residue. This is an aspartic acid, which is located at the tip of a loop, which is known as the portal loop. This loop opens to let the ligand get in and close when it is done, right? In our program MoproViewer, we can select this way. I selected actually 3 atoms of the carboxylate group of this particular aspartic acid. I computed electrostatic potential of the full protein using MoproViewer. I used point charges in this case, just for the example. And of course, I excluded the contribution of the ligand. So the tool we propose allows to select either electrophilic or nucleophilic influence zone, and user have access to various kinds of computation parameters, I would say. But usually default parameters are sufficient. So, sorry, let me hide this now. So the first thing which will be computed in our approach is, is this volume. This volume is actually the nucleophilic influence zone of the whole carboxylate group of this particular aspartic acid residue. It means in these orange volumes, all electric fields which are located in this volume, all of them converge to one of these 3 sites here. Or they fill the volume, which actually correspond to a large part of the binding site, up to the carboxylate head of the fatty acid. This is the first part. Of course, if all the line fields in this binding site converge toward this oxygen atom, they emanate from somewhere. Our algorithm show also all the electrophilic sites which are actually communicating, I would say, with these sites on the aspartic acid residue. So this orange volume contains all field lines emanating from these green spheres and converging toward this oxygen atom. And of course, all these are influence zones, so they are made of many primary bundles, right? And then our program allows also to show kind of abstract representations of the primary bundles in the forms of pseudo-line fields, kind of average line fields, characterizing each of the most prominent primary bundles in the binding pocket. And the radius of the abstract line fields correspond to the size of the bundle, actually. So what we can expect from this kind of representation is the following. Of course, I forgot to mention that all these are fully configurable, in MoproViewer. All bundles can be configured independently to each other, as well as the quality of the surface and so on and so on. So it shows actually that the ligand is under the influence of electric fields which exist in this form because of the closed position of the portal loop. The position of this particular oxygen atom allows the creation of this particular electrostatic environment. And of course, line fields going from plus to minus, this negatively charged carboxylate head is necessarily pushed in the direction of the bottom of the binding pocket because of this electrostatic environment. So this approach actually allows to pinpoint the role of distant sites within a binding pocket. So I will conclude now because I've been way longer, I guess. Conclusion. So about quantum crystallography methods applied to macromolecular systems. So obviously all this, what is published is by far dominated by studies based on transfer quantities, LMAM, UBDB, LMOS, polarizabilities now, thank you, Anna, and so on. Of course, it is these methods take the lion's share of what is actually published. Because the main reason is because they allow to get relevant biological conclusions. Large system are still, I think, quite out of reach of a more quantum-based approach, and the charge density refinement against protein subatomic resolution data is, how can I say, extremely difficult still, and the amount of available data set is not large enough to one. In terms of this potential influence zone, so it's just a mid paper, it provides an alternative representation of electrostatic properties in macromolecular structures. The implementation in our software do not depend on the choice of the potential map. We can use this from point charges, for multipolar map, for multipolar potential, or using Poisson-Boltzmann electrostatic potential, or whatever kind of map, as soon as it is written as a 3D scalar field, sufficiently fine sampled. This method highlights the 3D extent of electrostatic influence of any site in a given protein or given active site, in terms of electric forces, in terms of electric field, and in terms of possible polarization effects. It indicates the possible role of distant residues and the communication between them. And in terms of protein ligand complexity, this descriptor can be interpreted also to think about the binding forces between ligand and protein, and also about electrostatic steering effects, which will eventually lead to the binding between a small molecule and a ligand. And I would like to thank you for your attention, and I'm very sorry I'm a bit too long. Sorry about it.
Thank you, Benoit, for this excellent lecture, which is now open for comments and questions.
So,
Paulina has something to ask.
I'm looking for the chat.
Yeah.
No questions in the chat. Okay.
Not yet. Someone is typing. Okay.
I am.
Yeah, Benoit, I like very much this new work you presented about this analysis of electrostatic potential. The property which is really the most important one from the point of view how proteins are working, right? Like the binding, how the binding happens, but also how the enzymes are working. So beautiful tool.
Thank you.
Congratulations.
Thank you. So yeah, I have a question in the chat, I think.
Yes, from Hans Bedbirgi. So let's read this question.
Hello, Hans-Bet. Well, I think that the diffuse scattering problem is taken into account by most of the softwares designed to process X-ray diffraction data. In the classical way. And how do uncertainties in this separation translate into uncertainty of the direct space result? To be honest, it's a question I have to think about this a bit more. I would say, of course, the disorder has an effect on the thermal, on the diffraction intensities, which at the end translate into uncertainty on the parameters in the structure. But overall, the disorder in proteins is a problem in what we are doing globally, because we are looking for high resolution systems, and the higher the resolution, the more visible is the disorder, very typical stuff. So disorder is a problem because it has to be taken into account at any stage of the process, especially at the stage of the model preparation. In any of the studies I mentioned, there is a part which describes the way the model was prepared, and it has to be to be prepared very carefully with all the protons added, a very decent hydrogen bond network and so on. So I would say yes. I'm not sure I totally answered the question, but.
I have actually a following question. Have you computed this kind of influence zones for a series of similar structures, or the same protein but collected several times, just to see how it changed from one structure to another, from how it is sensitive to the tiny differences in atomic positions?
Yes, it's on its way, Paulina. You can imagine. Of course, it's on its way. We are looking to evaluate the relevance of this descriptor, for instance, in terms of residues or side chain variability, accounting maybe for molecular dynamic simulation, to see whether we can define some kind of influence zone fingerprint, but getting rid of the disorder, getting rid of the variability of the side chain position. So of course it's very important. And also one of the possible very appealing application would be the effect of point mutation on the landscape of the electrostatic landscape existing in a given active site due to a given mutation, on trying to correlate the biological effect of the mutation to what you observe in terms of this new descriptor. Totally, yes.
Benoit, going along the lines pinpointed by Hans-Beth, I wonder whether people are trying to refine protein structures using per distribution function type measurements and reverse Monte Carlo modeling later on. I mean, that would be really big problem, but for last year or so, I'm under influence of results obtained with per distribution function. And the advantage of this is that it takes not only the Bragg scattering information into account, but also this information in between the Bragg peaks and, of course, high resolution, high diffraction angle information. Do people do this kind of analysis for proteins, or it's still too difficult?
To the best of my knowledge, no, it's not the case. Or maybe I missed something, possibly, but I'm not aware of this, Christophe. I must confess. Yeah, I must confess. Well, so I always present attempts of refinement of electron density within protein structures, during my speeches. But the outcomes of this approach are, we must admit, maybe not as good as we would expect. But I want to add something about that, is that when we do high resolution charge density experiment or quantum crystallography experiment of small molecules, usually the diffraction data are collected for this purpose, especially for this purpose, which is never the case for proteins. So maybe a good step forward in this field, trying to obtain a true experimental model of aspherical electron density for protein, would be to try to grow crystals, to collect data, to process data in the very specific objective of doing a charge density experiment. And I think this is what was done by the Japanese people, by
Yeah, you are showing very nice examples of the use of different pseudo-atom data banks. There is one data bank somehow missing. In that sense that there is also, data banks based on refinement, and that I'm very keen on learning what would be advantage, what would be the gain in the case of Hirschfeld atom refinement type data banking applied to protein. Would be more more hydrogens? Would we see more, water molecules, more disorder, more other such effects?
Yes, maybe. I mean, if Hirschfeld et al. Refinement on all, even hybrid approaches which are developed around the objective of application on proteins, if these allow to improve the phase determination of proteins, it will improve the model itself. So it will improve, of course, the protons localization. It will improve the modeling of dual conformation, of even more than dual conformation sometimes, and so on. It is absolutely obvious. Yes. Yeah, I totally agree. The fact that these methods are not yet applicable to macromolecular structures does not hinder the fact that HAR has very good results in terms of especially hydrogen atom positioning. So applying these methods to macromolecular crystallography would be, of course, a very appealing perspective. Yes. But I think they have to parallelize the code a bit before. Because 9 days for a chromine is a bit too much. Well, you don't have to mess with the input file at the beginning, for sure.
Yeah, I do not see more questions, Paulina, unless you have some late one.
Not at the moment.
No, not at the moment. So then let us thank Benoit for his excellent.
Thank you very much.